Welcome back to ECE 442-542. This is installment C of lecture 6.2. This one is really just going to look at some example root loci and show you why these red lines are the root locus branches associated with each of these systems, and what we're trying to do now is just explain why they make sense or why they should be the root locus diagrams for each of these systems. And what you need to keep in mind is a root locus represents those points on the complex z-plane that actually satisfy the expression 1 plus k bar g bar of z. So now we're looking at 1 plus k bar, or k, g bar of z equaling 0. The values of z, as we adjust k is going to be between 0 and infinity, and we're going to let it go to infinity. And as we march k through different values from 0 up to positive infinity, what values of z cause this expression to be true? And we've learned or seen that k g bar of z is equal to minus 1, which is 1 at minus 180 degrees. If we're now looking at positive values of k, then we need the angle of g bar of z to equal minus 180 degrees, and that will then guarantee that those points, those values of z that satisfy this phase angle, will belong to the root locus. Let's now see how that's true for each of these different example systems and their associated diagram. The first system that we will look at is a first order system. We have one pole and it starts at z equal to 2. Root locus diagrams start on the open loop poles, that's where the x is, and they terminate on open loop zeros, finite zeros, and they go off to zeros at infinity. If we look at this particular system, we have no finite zeros and we have one zero at infinity. So this particular root locus diagram is going to begin at a value of z that causes z minus 2 to equal 0, or z is equal to 2, and it's going to then approach a 0 at infinity as k goes or approaches infinite in value, infinity. And what did we say? We're looking at the angle of these g bars, and in this particular case, if we look at this particular point, and if we are now at the pole, we would have to turn through 180 degrees to get to that location. We would have to turn through 180 degrees to get to that point. We would have to turn through 180 degrees to get to that point. All of these points that is actually shown by the red line, that's the one branch of the root locus, and it belongs on all real values of z from z equal to 2 all the way to z going off to minus infinity. That's as complicated as the root locus is for that particular diagram, or for that particular system. The second system is now similar, except now we've introduced one more pole. Now we have an extra pole at z equal to 0. Now, if we say every point on the root locus needs to have an angle of minus 180 degrees, we can start looking at some of these points. In this case, if we look at that point that I've highlighted in yellow, there's 180 degrees, and the pole at the origin contributes 0 degrees. That means every point on this segment of the real line or the real axis belongs to the root locus. But if this branch, and we have two poles, so we are going to have two branches. If this particular branch starts at 2, then it's either going to go up or down. Let's just say it goes down. Then the other branch starts at 0, and it will then go up. Now, why do we know that it's going to go up? And why does it make that right angle and then go directly up and down as we increase k from 0 to infinity? If we look at this particular triangle location, what's the phase or the angle contributed by both of those poles in combination? That angle is contributed by the pole at 2, and this angle is contributed by the pole at the origin. But the angle contributed by the pole at the origin is exactly the same as that angle that is supplementary to this angle, let's say theta sub p sub 2. So if we take theta sub p sub 2 and add the angle due to the pole at the origin, we are at 180 degrees. We are at that same angle value at any point on this line that's equidistant between 0 and 2. So that line goes vertical at z equal to 1. And every point on that line is belonging to the root locus. At the triangle, at the square, and at the cloud. All of those values have an angle on any point on that red line. These are just representative points or locations. What about the next curve or root locus? Now we have two poles, one at 2, one at 1. The line segment between 1 and 2 has an angle of 180 degrees. And there's two branches of the root locus. We have one branch here and another branch there. Suppose we say the blue branch now leaves. It can't stay fixed, and the yellow branch goes in the opposite direction. What happens next? Well, what we will learn is this particular root locus breaks away, and one goes around to the bottom and one goes around to the top. And in fact, it's a circle with the radius of that circle determined from the distance of that 0. The 0 is the center. The radius is determined by the geometric mean from the center to the pole, and from the 0 to each pole has a length, and we can now find the geometric mean of those two lengths, which in this case is what I'm calling r sub r. That's a distance of 1 from the origin to 1 and a distance of 2 from the origin to 1. So now we have the square root of 2 as our radius of that circle. And the reason we can make those claims is we know that the root locus starts on the poles, it terminates on finite zeros, and it goes off to zeros at infinity. In this particular system, we have 1 0 at infinity. One of those branches then needs to go off to infinity, and we have one finite 0, so that's why we have one of these branches stopping at the origin. Let's look at a more complicated. Now we have a third order. Now we have a third order system. We have a pole at 2, a pole at 1, and a pole at -1/2, and we have a 0 at the origin. We can find the values of the real axis or the line segments on the entire real line that belong to the root locus by looking at the phase angle condition. We can look at this particular point. Here is 180 degrees. This is 0, this is 0, and that's 0. So every point between 2 and 1 belongs to the root locus, and that's why it's red. any point between 0 and 1, we have an angle of 180 degrees here, an angle of 180 degrees there, and this one's 0 and that one's 0. We have two 180s, which is 360. That says then that there is no portion of the root locus on that line segment between 0 and 1. And that's why that line segment is not colored red. If we look at the line segment between -1/2 and the origin, now we have the two poles on the right making an angle of 180. We have the 0 making an angle of 180. We have 180 minus 180 minus 180. We're at minus 180, and the angle due to the pole at -1/2 is 0, and that's why we have a root locus branch between -1/2 and 0, because the phase anywhere, any point between -1/2 and 0 is minus 180 degrees. Any point on the real axis to the left of -1/2 has an angle of 0 degrees or 360 degrees, and so that does not belong to the root locus. How many finite zeros do we have? We have one. One of those three branches, we had three open loop poles, so we have three branches of our root locus. One of those branches is going to terminate or stop at the finite 0. The other two branches go off to infinity. And we'll learn why those angles are plus and minus 90 degrees, or plus 90 degrees and plus 270 degrees, as we learn more about the root locus sketching and diagrams. A couple more diagrams as examples. Suppose now we have a pole at 3/2 and another pole at -1/2 and a 0 at 1/2. We have an infinite 0, 1 0 at infinity. The branch to the left of -1/2 is going off to minus infinity. The line segment between 3/2 and 1/2, we can determine that it's actually belonging to the root locus because the angle at that any point is minus 180 degrees. That branch terminates at -1/2, and those are the only segments or branches of the root locus. They all belong on the real line. Likewise, we have another root locus diagram that is only restricted to the real axis. Here's a pole at 1/2, a 0 at 1, and a pole at the origin. Again, this particular 0 has an angle of 180, which is equivalent to minus 180. The two poles at any point between 1/2 and 1 have an angle of 0. That's why that particular line segment between 1/2 and 1 belongs to the root locus. Any point to the left of the imaginary axis, or on the left-hand side on the real line, belongs to the root locus because we have the 0's angle of 180. We have a pole having an angle to that point, which is 180. Those two subtract and are essentially canceled each other. And then we have the one pole at the origin, which from this pole to get to that point, he has to turn through an angle of 180 degrees. That's why these two branches are on the specific line segments that are shown in red, and we have one of those branches terminating at the finite 0. The other branch goes off to the 0 at infinity. We've now looked at a few representative root locus diagrams and why they make sense, basically based on the conditions that we know have to be true for a root locus. And those conditions all give rise to the rules that we are going to now develop but those conditions now are based on this magnitude of 1 and an angle of minus 180 degrees.